welcome to another exciting episode. Friday. It is Friday, March the 24th, the Friday before spring break. So everybody is very excited about being here. Okay? We're excited that this could be the last period before we have spring break. Let's go. All right. So, I made the decision yesterday that what I want to do with acids and bases in terms of the titration curves and acid-base titrations, I'm not going to be able to effectively even get a cram session in one day. So I thought it would behoove us more to kind of do a survey of what we've done so far all the way up to this point. In other words, let's review the year. The year in review, okay? In 45 minutes or less, okay? So, let's talk about stoichiometry, okay? That's probably the first main thing. We talked about atomic structure and all that, but that stuff's very basic and fundamental, and I'm assuming that we have that under control. But if I'm looking at stoichiometry, everything revolves around the mole, going to mole. Everything is just different conversion factors on how we take the given to moles. So if I'm given atoms or molecules or ions, how do you find out how many moles there are? Avogadro's number. Okay? 6.02 times 10 to the 23rd. All right, y'all, focus. Don't look at him. He would be. Okay, listen. All y'all.
Williams, right?
Hey, I got it. All right, here we go. I can barely. We're trying to do a whole year in 45 minutes. Okay, so we gotta rock and roll. So this could be atoms, this can be molecules, this can be ions, this can be whatever the given is to moles. Okay, we use Avogadro's number. And again, anytime something has 2 units on it, it's a conversion factor between those two things. Now, if I go from grams to moles, everybody in unison, grams to moles, who we use? That was not real strong unison, but molar mass. And the units on molar mass are always grams per mole. So, solution volume. This is what we just had to do in the lab that we just did. Solution volume to moles. How do you convert so many milliliters of silver nitrate to how many moles it is? What do we have to use? The molarity. And remember, that's capital, actually italicized M, and molarity are what units? Moles of solute over liters. So again, it converts solution volume, moles, and liters. What about gas volume at STP? That's when we use the 22.4, right? So that's 22.4. That's called the molar volume, which is equal to 22.4.
Hello.
Yes.
You have Kaylee Eloff
Yes.
to the front, please.
Okay. Are you checking out?
I think it's because he does the sound.
Oh, she's not checking out. All right. So. All right.
You'll be
So.
back. No, you'll be back.
You're fine. So, the molar volume means that if I have 1 mole of any gas, it doesn't matter whether it's hydrogen, oxygen, carbon dioxide, 1 mole of any gas at STP is going to occupy 22.4 liters. That means 2 gases at the same conditions of temperature and pressure. What is STP? I know, but what is it? I know, but what's the standard? What's standard temperature and what's standard pressure? 1 atm, 273 Kelvin, which is 0 degrees Celsius. 1 atm is how many torr? 760 millimeters of mercury. Okay? Now, the converse of that. That means, okay, so 1 mole of a gas, equal volumes, equal moles. 22.4 liters, 1 mole. But we don't always have 22.4 liters in 1 mole. But so Avogadro's principle says if I have 2 balloons, equal volumes, and one's hydrogen and one's carbon dioxide, one's oxygen, one's nitrogen, But if they're the same volume in their same room, same temperature, what does that mean about the number of molecules on the inside? The same. Equal volumes of gases under the same conditions of temperature and pressure contain the same number of molecules. That's Avogadro's principle. Now, because that means volume and moles are proportional, so if I want to make water and I have 10 liters of hydrogen, how many liters of oxygen do I need to combine it with? Go ahead, Cooper. 5. Because H2O, it's a 2 to 1, hydrogen to oxygen, right? So the volumes are going to be, 2 to 1. The volumes combine in the same ratio as the moles, because equal volumes contain the same number of molecules. That's Avogadro's principle. That kind of all goes with this molar volume. 1 mole of any gas at this specific temperature and pressure is going to occupy 22.4 liters. But that gives us a conversion factor between gas volume and moles, which makes the stoichiometry pretty simple. But if it's not at STP, what do we have to do? PV equals nRT, which would mean, so we use PV equals nRT, the ideal gas law. So N is PV over RT. So we have to, this is the only one we have to do in 2 steps. Most of the time on an AP test, they would break it up into 2 steps, ask you how many moles given the pressure, volume, and temperature, or ask you what the pressure was given a certain number of grams. Okay, so they can go all the way there. So we have all of these ways of converting. So let's just stick with gas laws. We did the molar mass of a gas. The lab that we did, we had the flask and we put the little bit of liquid in it, put it into the hot water bath, and then it vaporized, and we figured out then, okay, we then put it in the ice bath and recondensed it, so we knew the mass of the vapor. We knew the temperature because it was 100 degrees, it was in boiling water. We knew the volume, we had to figure out the volume, and that's where you guys filled it up with water and then, used a graduated cylinder and was able to figure out the actual volume of the flask. Because you need molar mass is GERT over PIV. And then how do we know what the pressure is? How would we know what the pressure of the gas was? Remember, it was a flask with a pinhole in it. So what did the pressure inside equal? The pressure on the outside, right? Now in Chemistry 1, those of you that had me last year, anybody? Okay, we did the lab where, and if you had Graber last year, okay, 2 years ago was COVID. I don't know if we did this lab or not, okay? But we did the lab where you pour in HCl into the bottom, and then we filled it to the tippy top with water, and then we turned it over, then we put a piece of magnesium metal. So if we have magnesium solid plus hydrochloric acid, HCl, what's that gonna make? Not just MgCl, what do we always have to make sure we do? Balance the charge. What's the charge on magnesium? Plus 2. What's the charge on chloride? Minus 1. So 2 plus and minus, so what's the formula?
MgCl2.
And then hydrogen is going to be H2, and it's a gas, and this is not one of our 3 chloride precipitates. Silver, lead, and mercury are the chloride precipitates. So our solubility rules, we would know that's aqueous. Now I balance it, I put a 2. So the reality is that we had a big beaker, okay? The HCl was up here and it worked its way down. The magnesium metal was right here. That's my magnesium. The acid worked, and then when they hit, what happened? What would we observe? Look at the equation. What would we observe? Now remember, this is all full of water. Okay? So I turn it upside down. This is all full of water, and the acid's working its way down. The magnesium's right here. When the acid hits the magnesium, what am I going to observe? Bubbles of hydrogen gas. Okay? So I'm collecting the gas by water displacement. So that's going to push now, as the bubbles up here, the water level comes down, comes down, comes down, comes down, comes down. Now, Does anybody remember what did we have to make sure happened in order to, when we were done? Does anybody remember what you had to do, what you had to make sure of? Those had Graver, you guys had it in a big graduated cylinder, okay? Nobody?
We were COVID year, or
Yeah.
some of us were COVID.
Okay, we had to make sure that once the water levels came down, that it ended where the water level was exactly the same inside the tube as it was outside, as it was in the beaker. Because what did that allow us to know?
Pressure inside is equal to pressure.
The pressure inside is the same as the pressure outside. So we collected, up in here, we collected the hydrogen gas. But if we collect it over water, is it only hydrogen up there?
No.
What else is up there?
Water vapor.
Water vapor. So what do we have to do? So the pressure of the atmosphere is equal to the pressure total, but the pressure total is equal to what?
H2O plus H2O.
Hydrogen and the water. So we got this from Siri, or they're supposed to read. In the olden days, we had actually had a barometer in here, but now we're not allowed to have mercury anywhere in the world. So we call Siri and let Siri tell us what the barometric pressure is. But how do I get the pressure of the dry gas? Subtract out the water vapor, which we get from the back of the book, or it's given in the problem, or whatever. It's dependent upon what temperature it is. So we use the pressure of the dry gas then to do any calculation. You remembering that? That's Dalton's law. Dalton's law of partial pressures. Okay? Just like in this room, right now, in this room, 78% of the molecules are nitrogen. So that means 78% of the collisions with you are nitrogen molecules, which means that 78% of the pressure on you is due to nitrogen. Since we're under 1 atmosphere of pressure, 0.78 atmospheres is due to nitrogen. 0.21 atmospheres is due to oxygen. The other 1% is due to argon, carbon dioxide, everything else. Okay? Somebody at the door? Oh, that's your jacket? We were wondering whose it was. Okay? We were wondering why somebody wore a jacket today, because it was like 80 degrees outside, so that was left here for a while. Okay? All right, so Dalton's law of partial pressures. The total pressure is the sum of the individual pressures. The part of each gas is the mole fraction. The percentage, again, it's 78% nitrogen, so 78% of the pressure, TJ. So if I have a mixture of gases where I have 3 moles of A, 2 moles of B, and 5 moles of C, okay, and the total pressure is equal to 800 millimeters of mercury. Well, what's the pressure of A going to be? What's
240.
3/10 of that?
3/10. It's going to be 3/10 times 800, which Zach did in his head was 240. Okay, let's do an easier one. Pressure of C. 5/10, right? So it's 400. So it's always just the partial pressure. Okay, that Raoult's law. Okay, so that's your gas laws. I think I've covered just about everything that we covered with gas laws. PV equals nRT is by far the most important of that. Okay, but Dalton's law comes into play when in an experiment, when you collect things over water, and then just kind of go from there. So now let's talk a little thermo. Delta H, enthalpy. We translate that to mean heat. Okay, heat of reaction. It could be heat of formation, heat of combustion. The heat of formation is the energy that is released or absorbed when a compound is made from its elements. Now, there are a bunch of different ways in which we can use the delta H or calculate the delta H. The first one, to kind of keep in the stoichiometry trend, if delta H is kilojoules per mole, what's that a conversion factor between? Kilojoules and moles, right? So if we do a problem and just use a simple equation again, we just use, let's just go ahead and use this equation that we just did with the 2HCl. Okay, but we say if 10 grams of magnesium reacts with HCl, and we measure it and we find that the delta H of this is equal to 500 kilojoule, 5,000 joules is released, negative. Okay, so first off, negative, endo or exothermic? Exothermic. So what is the solution getting hot or cold? It's getting hot. Remember, the energy, the potential energy of the system is going down. Well, where's that energy going? To the surroundings. So the surroundings is getting hot, right? So we're observing the surroundings hot, but we're measuring the system. Q lost, the system, is equal to negative Q gained by the surroundings. The surroundings are gaining energy, getting hot. We take the negative of that, that's how much energy was released then by the system. Potential energy, bonds breaking, bonds forming, turned into kinetic energy, temperature. All right, we spent a lot of time talking about that. So, if that's the case, the question is then, what is delta H of the reaction in kilojoules per mole? How do we do that? Okay, TJ, you're saying what?
You need to break the joules to kilojoules.
Okay, so we can just do that in our head, right? So how many kilojoules is that going to be?
5.
-5, and let's just say, and we'll do that. So it's going to be -5.000 kilojoules. But that's per how much?
10 grams of magnesium.
Per 10 grams of the magnesium. Okay? So how do I get it to kilojoules per mole? Times the molar mass of the magnesium, so times 24.3 grams over 1 mole. And that's going to give me, you know, the whatever that comes out to, kilojoules per mole.
It's like 12.5.
25 times 5 is 125, divided by 10 would be 12.5, so it's going to be a little bit less than 12.5, so let's estimate 12.3.
12.15.
12.15, 12.2. All right, we'll go with 12.2. Close enough for government work. Okay, the whole point is that we need to be able to do the stoichiometry. We could go the other way. If the delta H is kilojoules per mole, how much energy is going to be released when 10 grams burns? So we change grams to moles and then multiply it by the kilojoules per mole. Make your units work. Follow the units. The units are your friend. Delta H of a reaction is kilojoules per mole reaction. Now remember that if we're dealing with a reaction like 2H2 plus O2 goes to 2H2O, and they say delta H of the reaction is equal to, say, 100. Well, that's 100 kilojoules or 100 joules, whatever the unit is. Let's even say if it says kilojoules per mole reaction, that's per 2 moles of H, per 1 mole of O2, or per 2 moles of water formed. It's per mole reaction, whatever is written. Okay, so that's how we use the delta H for stoichiometry. You might want to go back, and I just put on Classroom a plethora of review materials, okay, for your study pleasure. Probably the best one is probably going to be the PowerPoint, but it's like 100-something slides, but it goes through the whole year, and a PowerPoint does practice problems through everything on there. Now, there's 2 areas we're going to get when we get to acid-base titrations and titration graphs and all of that. What's the pH at a certain point in a titration? We haven't done that yet. We're going to do that as soon as we come back. If they ask anything about electrochemistry, voltage, E cell and all that. We're gonna do that when we come back. Crash course. Then we're gonna try and review somewhat, okay?
Isn't H2 and O2 exothermic reactions?
Yeah, it'd be a negative 100. Yeah, it would be. Okay, I'm just throwing up numbers just to get an example. Okay, now, listen. You guys sometimes get confused between these two, when to use them. This is whenever they give you bond energies. A carbon-to-carbon single bond has a certain bond energy, the energy needed to break the bond. If they give you bond energies, use this one. If they give you the heats of formation, you use this one. But this is given on the equation sheet. This one is not. All of these are products minus reactants. This one, remember, this one is reactants, and this one is products. This one's backwards from all the other ones. Bonds broken minus bonds formed. This one is not on the equation sheet. But if you're given bond energies, use this one. If you're given heats of formation, you're given this one. Now, in both cases, there are two different ways they give the problem. They'll either give you all of your heats of formation, all your chemicals, and ask for the delta H from the chemical reaction, or they'll give you the delta H of the reaction, and you have to find one of the delta H of formation. They give you 3 of the 4, and you have to find the 4th one. Remember, you multiply by your coefficients. And what's the heat of formation of an element? Delta H of an element? 0. Okay? This one, bonds broken minus bonds formed. They may give you delta H. You have to find an individual delta H of the bond energy. Again, if it's 3 times X, they want the value of X, not 3 times X. Okay, so whatever the coefficient is, you got to include that in your equation there. Okay? Hess's law, does anybody remember what Hess's law says? If you add the equations, the delta H's add. Okay? What do you do if you flip an equation? No, that's K. Because here, remember, it's products minus reactants. So if I swap the equation, it's just going to change the sign, right? What if I multiply the equation by a coefficient? Like this one, I went to 1 H2 plus a half goes to 1 water. What do I do to delta H? No, that's a K. That's K. You multiply by the 1/2. Okay, whatever you do to the equation, you multiply delta H. Okay, because you multiply the coefficients, multiply 3, So this would be 2 times, well, this wouldn't have 1, but it'd be 2 times 0 plus 1 times 0, and this would be 2 times the heat of formation of water. And then calorimetry problems. We did a lot of calorimetry problems. This is Q loss equals negative Q gain. Your delta H of your reaction is going to give you the negative mass specific heat of the solution. Now, if the substance is dissolving, reacting in the solution, you add the water plus the reactant. But if it's just a metal in the solid, then it's not only the water is getting hot. Okay, so it all depends upon how it's worded on whether or not but they'll give you the specific heat of the solution. What's M stand for? And delta T? Does it have to be in Kelvin? Since it's delta T, it's no. If it's just T, like PV equals nRT, yes. Delta T is no. This is where, again, a lot of times, this answer will come out in joules. This is where then you'll have to take it, joules per however many grams reacted to cause that heat change. You get that many joules per gram, and then you have to change it to kilojoules per mole. This is when that happens a lot. Remember that? Everybody said a resounding yes.
Yes.
I remember, because Mr. Hobbs, you taught me so well. Okay? And I love it so much. I just review it all the time. I live in a utopian world. All right. So then entropy. Entropy. Entropy is, we calculate products minus reactants. Now, on this one, remember, elements do have an entropy. So, but what unit is entropy generally calculated in, joules or kilojoules? Joules. All right? And so you do products minus reactants. Again, they could give you the entropy of the reaction, and you have to find the individual entropy, or they give you all the entropys, you find the entropy of the reaction. But it's products minus reactants again. But then we have delta G, and what is the significance of delta G?
Tell you if it's
thermodynamic.
Spontaneous or not? What's the sign if it's spontaneous? Thermodynamically favorable.
Negative.
Negative. All right, it's the ultimate determiner. Now we have delta H. What's the favorable sign
Negative.
for delta H?
Negative.
Negative. What's the favorable sign for delta S? And how can I look at a reaction and know if delta S is going to be positive or negative?
There's more gases on the products.
You look at moles of gas only, moles of gas. If moles of gas is increasing, then we're gonna have an increase, a positive delta S. If moles of gas is decreasing, a negative delta S. Which one's favorable? Positive or negative? Positive is favorable. Positive delta S. A negative delta H, exothermic reactions, because everything wants to be in the lowest possible energy state. But they want to have the most micro states. They want to have the most disorder. They want to have the most possible rearrangements. And when you go from a solid to a liquid to a gas, a liquid has more rearrangements, more possible arrangements of the molecules. And then you go to a gas, you have more possible arrangements of the molecules. AP kind of likes you to say it more like that than they do saying chaos or disorder. I think chaos and disorder is a much simpler, legitimate way to say it, but it's more micro states. The more possible arrangements is the increase in entropy. Okay, now the key to this equation, delta G is measured in what unit? Kilojoules or joules?
Kilojoules.
Delta H, kilojoules or joules? Kilojoules. Delta S, kilojoules or joules? Joules. So we plug this in. Now T in this one, Celsius or Kelvin? Is it a delta?
No.
No, it's got to be Kelvin. It's got to be Kelvin. Okay? If it's delta, a change in temperature will be the same, Celsius or Kelvin. But if it's just T, it's got to be Kelvin. Students miss this one because they don't get the units matched. Usually I make this one, just change this into kilojoules, and then the answer will come out in kilojoules. Or if you have delta G and you have to find one of these, just follow your units. The units are always given, just make sure they match. But in this equation here, and then we just did this one on our last test, delta G is equal to negative RT natural log of K. What is the value of R that we use on this one? 8.31, but it's joules. This is kilojoules. 8.31 is given on your equation sheet. The unit is given on the equation sheet. You just have to make sure the units match. If you're given delta G looking for K, then R and G have to be in the same unit. If you're given K looking for G, then know that it's going to come out in joules, and you always make sure you put a unit on it, because if you just say a certain number but you don't specify if it's joules or kilojoules, even though you got the right number, you don't get credit. All right, so make sure you put your unit. Make sure the units match. Then we have the chart. Okay, so if we have delta H, delta S, and then delta G, our four scenarios. Okay, what's the favorable again for delta H sign?
Negative.
Negative. Exothermic. What's the favorable sign for delta S?
Positive.
So delta G is equal to delta H minus T delta S. So this is positive. So what's delta G gonna be on all temperatures?
Always negative.
Always negative, always spontaneous, always thermodynamically favorable. But what's the reverse of that gonna be?
Positive, negative, positive.
Positive, negative. Neither one is a favorable change. So when we look mathematically, a positive minus a minus is always going to give me a positive. That one is never going to happen, no matter what the temperature is. Now, what if they're opposite though? What if it's minus and minus?
Negative at low temperatures.
So now it can be positive or negative. It's going to be spontaneous when?
Low temperatures.
At low temps. Okay, so we remember negative and negative, low temps. That's when it's spontaneous. But we have to answer it in terms of delta H and T delta S. So if delta H is exothermic, then at some temperature T, the T delta S term is going to get great enough to where a minus and a minus, that's going to cause delta G to be positive and the reaction to become non-spontaneous. So it's only going to be spontaneous at low temperatures. On the other hand, if I say positive, positive, this is going to be spontaneous when? At high temperatures, again. Answer it here. So you have a positive delta H, which is unfavorable, but at some point, at some temperature T, the T delta S term will become greater than the delta H term, causing delta G to become negative and the reaction to be spontaneous. You must explain it in terms of all those factors. Right? Just said something I wanted to say. Oh. A question that almost always goes along with this. Okay? A reaction is thermodynamically favorable. Delta G is negative, but the reaction doesn't occur. Why not? So what? Energy of activation. Let's just maybe put it into a whole sentence. Why would a reaction that has a negative delta G, like this paper, why is it not bursting into flames? It's got hot at room temperature. There's not enough energy in the molecules to overcome the activation energy. Okay? Now, that just takes us to kinetics. What must have to happen in order for it to be an effective collision, in order for this to turn into... Okay, you guys are great with words and phrases. How about sentences?
Molecules must.
Okay, Zach, go ahead.
Reactant molecules must collide with proper collision to where reactant bonds begin to break and product bonds begin to form.
Okay, the proper orientation, the proper arrangement for reactant bonds begin to break and product bonds begin to form. That's one. What's the second criteria? Sufficient energy to overcome EA. Right? So right now at room temperature, there's not enough energy to overcome. Most molecules don't have enough energy to overcome EA. Once every blue moon they do. So when I pull out my ancient college notebooks, they do look like they've been in a fire, because over the past 3 years, every once in a blue moon, a molecule has enough energy in the proper orientation to where it does oxidize the paper, and so the reaction occurs, but very slowly, not observable. It takes a long, long, long time. Okay? So, now, in kinetics, we have the reaction mechanism. What do we call the slow step? The rate determining step. And remember, it's an elementary step. What you see is what you get. In a mechanism, the individual steps. So what must be true about that reaction mechanism? What 2 criteria for it to be effective?
It adds up to the original.
It has to add up, all the individual steps have to add up to the original equation that you're trying to describe. And the rate law of the slow step, the rate determining step, has to be the same as the experimentally determined rate law. Okay? Now, so that means that the coefficients, that slow step, that because we have to have proper orientation, is it likely that 3, 4, 5 molecules can all collide in the proper orientation? Is the probability very high that you can get 4 molecules all to hit the proper orientation? No, so most elementary steps in a mechanism are going to be either a unimolecular, one molecule having to just break apart, having some ultraviolet radiation hit it, breaks the bond apart, or a bimolecular, where 2 molecules collide with the proper orientation and then form some intermediate that then can continue on in the reaction. And remember, an intermediate, where is it formed in the mechanism?
It's first in the products and then it's a reactant.
Is an intermediate a reactant or a product?
No.
It's something formed in the middle. It's an intermediate substance. Okay? It's formed and consumed in the middle. Where's a catalyst going to be in your mechanism? Start as a reactant, end as a product. So it cancels out, so it's not in the overall equation, but it was added and then reformed. So where does it normally go if you write an equation? Over the arrow. Okay. Now let's look at, Lewis structures. Do we remember how to do Lewis structures? Okay, so let's look at H2SO4. H2SO4, what's the first thing we need to do? Count the electrons. 2 plus 6 is 8, plus 24, I have 32 electrons. So I have sulfur. When I have hydrogen and oxygen. Hydrogen's on the oxygen, not on the central atom. How many each single bond represents how many electrons? 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I counted, that's 32, I counted wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24.
Should be oxygen, like you have 3 hydrogens.
Oh, that's right, there we go. I knew something was screwy, thank you. There we go, so there's 32. Okay, now, that's the way we would draw it if it just said draw a Lewis dot structure. But every once in a blue moon, they ask for this thing called formal charge. Y'all remember that? Okay?
Away at the bottom.
Okay, that's the optimal way. We want to minimize the formal charge. Okay, we want it to go down as low as possible. So, remember the formula is the number of valence electrons minus 1/2 bonding electrons minus total non-bonded, lone pair, non-bonded electrons. So in this one, let's say that we have this is oxygen 1, this is oxygen 2. These are both the same, these are both the same. So if I want to start with hydrogen, okay? How many valence electrons does hydrogen have? Hydrogen has how many valence electrons? 1. Minus, we're just looking right here, this is two electrons, right? But hydrogen only gets credit for 1 of them, minus 1/2 of 2, minus 0, it's 0. That's good. We like formal part charge to be 0 is good. Okay? We look at sulfur. Sulfur has 6 valence electrons, minus 2, 4, 6, 8, minus 1/2 of 8, no lone pair on it, so it's plus 2. That's not so good. Okay? Then we can do oxygen 1. Oxygen 1 has 6 minus 1/2 of 4. Minus 4 is equal to 0. Well, we like that. But oxygen 2 is 6 minus 1/2 of 2 minus 6 is equal to minus 1. Okay, oxygen 2. 6 minus 1/2 of 2 minus 6. Okay? So, when you have a minus and a plus, we need to steal from the rich, share with the poor. We need to steal from the negative, give to the positive. We want to minimize our formal charge. So, we're just going to take 2 from here, form a double bond, 2 from here, and form a double bond. Now when you do that, now this is 6. This one now is 6 minus 1/2 of 4 minus 4. It's the exact same thing as this one now. So this one goes to 0. And this one now is 6 minus 1/2 of 12 minus 0 is equal to 0. So it goes to 0 as well. So according to formal charge, this is the better structure. The one with the minimal formal charge on every element close to 0. Okay? Now I heard Charlie joke about the shape. We do need to know shapes. Okay, now you wouldn't have to know that one, but you would have to know this. AX4, tetrahedral. AX4 is going to be what type of hybridization? sp3. Okay? So AX3 is going to be what type of hybridization? sp2. And AX2 is going to be sp. We are sp. Okay? So, all right, 4 minutes. Okay? Now, y'all, you just have to know that formula. Don't give up on me, y'all. 4 minutes. 4 minutes. Y'all gave up on me a long time ago?
When did we start this year?
All right. This is phenylamine or something benzylamine, something amine. Okay? Since it's got this Na, NH2, what do you think? Is this going to be an acid or a base?
Base.
A base. So what's it going to make? OH minus and C6H5 NH3 plus. Now, if we start with a 0.10 molar of this, and we're told that the pH at equilibrium, the pH is equal to 11.5. What is, well, let me write it down lower here. pH is equal to 11.5. What is Kb? What is Kb? How do I do that? What does this pH tell me? If I know pH, what do I know? I know the pH, I know the H+, but I also know the POH. What do I need to know for Kb? It's going to equal C6H5 NH3 plus times OH minus all over C6H5 NH2. So if I need Kb, I need all of these values. So how do I get that? Ice, baby. Okay, so this is 0 and 0. What's my change? What at equilibrium, what do I know?
It's 0.10 molar minus X.
Minus X, but I can't have two variables if I'm looking for Kb. I can't have an X. What does pH tell me? What's the POH? 2.5. Well, how can I use that? No, 10 to the negative 2.5 is going to equal what? What concentration? That's the OH minus. Someone get that value for me, please. 0.0032, good. Okay? So that tells me at equilibrium, this is 0.0032. What does that make this one? 0.0032. What does that make this one? Minus 0.0032. So that's what you put into here, and you can get your value of Kb. So if you know the pH, you know the POH. If you know the pH, you know the H+. If you know the POH, you know the OH minus. This is just like our equilibrium. We did it a lot with acids. We didn't do very many with bases. We're going to do more when we come back from spring break. And just do a lot of practice problems with the acids and bases. All right. Y'all have a wonderful spring break. Be good. If you can't be good, be careful. Okay, make wise decisions. They last with you a lifetime.